Today let us have a discussion on ring homomorphisms. We will find how many ring homomorphisms are there from set to set, from set to set cross set, from set cross set to set, and from set cross set to set cross set. So let's go to the class. Find all ring homomorphisms from set to set. We know that phi from R to R dash is a ring homomorphism if it satisfies two conditions. Phi of x plus y equal to phi of x plus phi of y and phi of x into y equal to phi of x into phi of y for all xy belong to R. Here we have to find all ring homomorphisms from set to set. That is, we have to take an n belong to Z and we have to define what will be phi of n. Actually, we know that phi of n can be written as phi of n into 1. So this is actually phi of 1 plus phi of 1 plus etc. plus phi of 1 n times. Or we can write equal to n into phi of 1. So if we define the image of 1 under phi, we can define phi of n for any n belong to set. So it is actually enough to define phi of 1 to define the ring homomorphism phi. Now phi of 1 can be written as phi of 1 into 1. And this is equal to, by homomorphism property, this is phi of 1 into phi of 1. So actually phi of 1 is an element in set such that phi of 1 equal to phi of 1 square. Therefore, phi of 1 is an element in set such that phi of 1 equal to phi of 1 square. So what are the possibilities for phi of 1? We have to find an integer whose square is the integer itself. Therefore, phi of 1 can be 0 or 1 because 0 square is 0 itself and 1 square is 1 itself. So for phi to be a ring homomorphism, 1 should be mapped to either 0 or 1. Now suppose phi of 1 equal to 0. Then what will be phi of n? Phi of n is actually n into phi of 1. So that's equal to 0 for all n belong to set. So here the map phi is the trivial map. That is mapping all the elements of set to the element 0 in set. And if phi of 1 equal to 1, then phi of n equal to n into phi of 1. That's equal to n into 1 which is equal to n for all n belong to set. Here phi is the identity map, mapping each element of set to itself. Therefore, only ring homomorphisms phi from set to set are the trivial map mapping all the elements of set to 0 and the identity map in which all the elements of set are mapped to itself. So there are two ring homomorphisms from set to set. Now let us find the ring homomorphisms from set to set cross set. Here we will take an element n belong to set and we have to find the image of n under the map phi to define the ring homomorphism phi from set to set cross set. Here we know that phi of n can be written as phi of n into 1. So that's equal to n into phi of 1. So as in the previous case, it is enough to define the image of 1 under phi to fix the ring homomorphism phi from set to set cross set. Just as in the previous case, phi of 1 equal to phi of 1 into 1 which is equal to phi of 1 into phi of 1. So that's equal to phi of 1 square. Here phi is a map from set to set cross set. So actually phi of 1 is an element in set cross set. Let phi of 1 equal to n1 n2 belongs to set cross set. So what is the property of n1 n2? n1 n2 square should be equal to n1 n2 itself. So which are the possible pairs for n1 n2 in set cross set such that n1 n2 square equal to n1 n2 itself? The possibilities are 1 0, 0 1, 1 1 and 0 0. For example, if we take 1 0 square, it is actually equal to 1 0 into 1 0. So that's equal to 1 into 1 is 1 itself, 0 into 0 is 0. So 1 0 square is 1 0. Likewise, 0 1 square equal to 0 1, etc. So the only possibilities for phi of 1 are 1 0, 0 1, 1 1 or 0 0. Now first case is phi of 1 equal to 1 0. So what will be phi of n? It's equal to n times phi of 1. That is n times 1 0, that's equal to n 0. And the second possibility is phi of 1 equal to 0 1. Then phi of n becomes n into phi of 1, that is 0 n. Third case is phi of 1 equal to 1 1. In which case phi of n is equal to n n. And in the last case phi of 1 equal to 0, 0. And here phi of n equal to n times phi of 1, which is also equal to 0, 0. Therefore, these are the only ring homomorphisms from set to set cross set. So there are 4 ring homomorphisms from set to set cross set. Now we are going to find the ring homomorphisms from set cross set to set. So we have to define ring homomorphism phi from the ring set cross set to the ring set. So we have to choose an element nm belong to set cross set, and we have to define phi of nm. And what is phi of nm? It can be written as phi of n0 plus 0m. By the first property of ring homomorphism, is equal to phi of n0 plus phi of 0m, which is equal to n times phi of 10 plus m times phi of 01. So, to define phi of nm for any integer nm belong to set, it is enough to define phi of 10 and phi of 01. Here, just as in the previous cases, phi of 10 equal to phi of 10 into 10. Since 1 is equal to 1 into 1, that is 1, 0 into 0 is 0. So, this is equal to phi of 10 square. So, we have to define phi of 10 as an integer in set such that square of the integer gives the integer itself. So, the only possibilities of small r are 1 and 0. Therefore, phi of 10 can be either 1 or 0. Now, we have to define phi of 01 also. We may notice that phi of 10 into phi of 01 equal to phi of 10 into 01 using the second property of ring homomorphism. And what is the product here? 10 into 01 is 0, 0. Therefore, we have phi of 10 into phi of 01 equal to phi of 0, 0. And we know that under a ring homomorphism, the additive identity element in the first ring is mapped to the additive identity element of the second ring. Therefore, here phi of 0, 0 is equal to 0. So, we have already predicted the values of or the possible values of phi of 10, and we have to find phi of 01 such that phi of 10 into phi of 01 gives 0. So, if we choose phi of 10 as 1, then phi of 01 should be 0 because 1 into 0 gives 0. Similarly, if we choose phi of 10 as 0, then phi of 01 may be 1 or 0, since 0 into 1 is 0 and 0 into 0 is also equal to 0. Therefore, we have to consider 3 cases here. First case is phi of 10 equal to 1 and phi of 01 equal to 0. Then we will get a ring homomorphism phi from set cross set to set satisfying these two conditions. Similarly, we have second case is phi of 10 equal to 0 and phi of 01 equal to 1. And the third case is phi of 10 equal to 0 and phi of 01 equal to 0. So let us go through each of these cases. Case 1, phi of 10 equal to 1 and phi of 01 equal to 0. Then phi of nm equal to n into phi of 10 plus m into phi of 01, that is phi of nm equal to n into 1 plus m into 0, that is equal to n. In the second case, phi of 10 equal to 0 and phi of 01 equal to 1. Then we get phi of nm equal to n into 0 plus m into 1. That is phi of nm equal to m. And in the third case, phi of 10 equal to 0 and phi of 01 also equal to 0. Then we get phi of nm equal to n into 0 plus m into 0, that is equal to 0. So these are the only 3 ring homomorphisms from set cross set to set. Therefore, there are 3 ring homomorphisms from set cross set to set. Finally, let us find the ring homomorphisms from set cross set to set cross set. Just as in the previous case, phi of nm can be written as n into phi of 10 plus m into phi of 01. Therefore, it is enough to define phi of 10 and phi of 01 to fix phi of nm. Here also phi of 10 equal to phi of 10 into 10, that is phi of 10 into phi of 10, which is equal to phi of 10 square. Therefore, phi of 10 is an element in set cross set such that its square gives the same element. So the possibilities of phi of 10 are 10, 01, 00 and 11. Similarly, the possibilities for phi of 01 are again 10, 01, 00 and 11. Like in the previous case, we note that phi of 10 into phi of 01 is phi of 10 into 01, that's equal to phi of 00, which should be equal to 0. So we will consider the different cases. First case is phi of 1 0 equal to 1 0. Then the possibilities for phi of 0 1 are 0 1 and 0 0. Since 1 0 into 0 1 gives 0 0 and 1 0 into 0 0 also gives 0 0. Similarly, in the second case, we take phi of 1 0 as 0 1. Then the possibilities for phi of 0 1 are 1 0 and 0 0. Third case, phi of 1 0 equal to 0 0. Then the possibilities for phi of 0 1 are 1 0, 0 1, 1 1 and 0 0. So there are 4 possibilities for phi of 0 1 if we fix phi of 1 0 as 0 0. And in the last case, if phi of 1 0 equal to 1 1, then phi of 0 1 can only be 0 0. Because 1 1 into 0 0 gives 0 0 and there is no possibility for phi of 1 0 such that phi of 1 0 into phi of 0 1 gives 0 0. So according to the first case, there are 2 ring homomorphisms from set cross set to set cross set. Second case gives again 2 ring homomorphisms from set cross set to set cross set. If we fix phi of 1 0 as 0 1 and if we fix phi of 1 0 as 0 0, there are 4 ring homomorphisms from set cross set to set. And if we fix phi of 1 0 as 1 1, there is 1 ring homomorphism satisfying this case. So altogether there are 9 ring homomorphisms from set cross set to set cross set. So let us stop the discussion here. Thank you.